Islamic astronomy comprises the astronomical developments made in the Islamic world, particularly during the Islamic Golden Age, and mostly written in the Arabic language. These developments mostly took place in the Middle East, Central Asia, Al-Andalus, and North Africa, and later in the Far East and India. It closely parallels the genesis of other Islamic sciences in its assimilation of foreign material and the amalgamation of the disparate elements of that material to create a science with Islamic characteristics. These included Greek, Sassanid, and Indian works in particular, which were translated and built upon. In turn, Islamic astronomy later had a significant influence on Byzantine and European astronomy, as well as Chinese astronomy and Malian astronomy. A significant number of stars in the sky, such as Aldebaran, Altair and Deneb, and astronomical terms such as Alidade, Azimuth, and Nadir, are still referred to by their Arabic names. A large corpus of literature from Islamic astronomy remains today, numbering approximately 10,000 manuscripts scattered throughout the world, many of which have not been read or catalogued. Even so, a reasonably accurate picture of Islamic activity in the field of astronomy can be reconstructed. History. Introduction. Ahmad Darnell notes that, unlike the Babylonians, Greeks, and Indians, who had developed elaborate systems of mathematical astronomical study, the pre-Islamic Arabs relied entirely on empirical observations. These observations were based on the rising and setting of particular stars, and this area of astronomical study was known as Anwar. Anwar continued to be developed after Islamization by the Arabs, where Islamic astronomers added mathematical methods to their empirical observations. According to David King, after the rise of Islam, the religious obligation to determine the Qibla and prayer times inspired more progress in astronomy for centuries. Donald Hill divided Islamic astronomy into the four following distinct time periods in its history: the period of assimilation and syncretization of earlier Hellenistic, Indian, and Sassanid astronomy. The first astronomical texts that were translated into Arabic were of Indian and Persian origin. The most notable of the texts was Zij al-Sindand, an 8th century Indian astronomical work that was translated by Muhammad ibn Ibrahim al-Fazari and Yaqub ibn Tariq after 770 CE with the assistance of Indian astronomers who visited the court of Caliph al-Mansur in 770. Another text translated was the Zij al-Shah, a collection of astronomical tables compiled in Sassanid Persia over 2 centuries. Fragments of text during this period indicate that Arabs adopted the sine function in place of the chords of arc used in Greek trigonometry. 825-1025. This period of vigorous investigation, in which the superiority of the Ptolemaic system of astronomy was accepted and significant contributions made to it. However, Darnell notes that the use of parameters, sources and calculation methods from different scientific traditions made the Ptolemaic tradition receptive right from the beginning to the possibility of observational refinement and mathematical restructuring. Astronomical research was greatly supported by the Abbasid Caliph al-Ma'mun through the House of Wisdom. Baghdad and Damascus became the centers of such activity. The caliphs not only supported this work financially, but endowed the work with formal prestige. The first major Muslim work of astronomy was Zij al-Sind by al-Khwarizmi in 830. The work contains tables for the movements of the Sun, the Moon and the 5 planets known at the time. The work is significant as it introduced Ptolemaic concepts into Islamic sciences. This work also marks the turning point in Islamic astronomy. Hitherto, Muslim astronomers had adopted a primarily research approach to the field, translating works of others and learning already discovered knowledge. Al-Khwarizmi's work marked the beginning of non-traditional methods of study and calculations. In 850, Al-Farghani wrote Kitab Fihuani. The book primarily gave a summary of Ptolemaic cosmography. However, it also corrected Ptolemy based on findings of earlier Arab astronomers. Al-Farghani gave revised values for the obliquity of the ecliptic, the precessional movement of the apogees of the Sun and the Moon, and the circumference of the Earth. The book was widely circulated through the Muslim world, and even translated into Latin. 1025 to 1450, the period when a distinctive Islamic system of astronomy flourished. The period began as the Muslim astronomers began questioning the framework of the Ptolemaic system of astronomy. These criticisms, however, remained within the geocentric framework and followed Ptolemy's astronomical paradigm. One historian described the work as a reformist project, intended to consolidate Ptolemaic astronomy by bringing it into line with its own principles. Between 1025 and 1028, Ibn al-Haytham wrote his Al-Shukuk al-Batlamyas. While maintaining the physical reality of the geocentric model, he criticized elements of the Ptolemaic models. Many astronomers took up the challenge posed in this work, namely to develop alternate models that resolved these difficulties. In 1070, Abu Ubaid al-Jusjani published the Tariq al-Aflak. In his work, he indicated the so-called equant problem of the Ptolemaic model. Al-Jusjani even proposed a solution for the problem. In Al-Andalus, the anonymous work Al-Istidrak al-Batlamyas included a list of objections to the Ptolemaic astronomy. Other critical astronomers include Muayyad al-Din al-Urdi, Nazir al-Din al-Tusi, Qutb al-Din al-Shirazi, Sadr al-Sharia al-Bukhari, Ibn al-Shatir, and Ali al-Kushji. The period of stagnation, when the traditional system of astronomy continued to be practiced with enthusiasm, but with rapidly decreasing innovation of any major significance. A large corpus of literature from Islamic astronomy remains today, numbering around some 10,000 manuscript volumes scattered throughout the world. Much of this has not even been catalogued. Even so, a reasonably accurate picture of Islamic activity in the field of astronomy can be reconstructed. Influences in East Asia. China. Islamic influence on Chinese astronomy was first recorded during the Song dynasty, when a Hui Muslim astronomer named Ma Yi's introduced the concept of 7 days in a week and made other contributions. Islamic astronomers were brought to China in order to work on calendar making and astronomy during the Mongol Empire and the succeeding Yuan dynasty. The Chinese scholar Lu Chutzai accompanied Genghis Khan to Persia in 1210 and studied the calendar for use in the Mongol Empire. Kublai Khan brought Iranians to Beijing to construct an observatory and an institution for astronomical studies. Several Chinese astronomers worked at the Maragha Observatory, founded by Nazir al-Din al-Tusi in 1259 under the patronage of Hulagu Khan in Persia. One of these Chinese astronomers was Fu Menqi, or Fu Mejai. In 1267, the Persian astronomer Jamal ad-Din, who previously worked at Maragha Observatory, presented Kublai Khan with 7 Persian astronomical instruments, including a terrestrial globe and an armillary sphere, as well as an astronomical almanac, which was later known in China as the Wanyanli. He was known as Jamaluddin in China, where, in 1271, he was appointed by Khan as the first director of the Islamic Observatory in Beijing, known as the Islamic Astronomical Bureau, which operated alongside the Chinese Astronomical Bureau for 4 centuries. Islamic astronomy gained a good reputation in China for its theory of planetary latitudes, which did not exist in Chinese astronomy at the time, and for its accurate prediction of eclipses. Some of the astronomical instruments constructed by the famous Chinese astronomer Guo showed emerging shortly afterwards resemble the style of instrumentation built at Maragall, in particular the simplified instrument and the large gnomon at the Gaocheng Astronomical Observatory show traces of Islamic influence. While formulating the Shoshili calendar in 1281, Shojing's work in spherical trigonometry may have also been partially influenced by Islamic mathematics, which was largely accepted at Kublai's court. These possible influences include a pseudo-geometrical method for converting between equatorial and ecliptic coordinates, the systematic use of decimals in the underlying parameters, and the application of cubic interpolation in the calculation of the irregularity in the planetary motions. Honggu, emperor of the Ming dynasty, in the first year of his reign, conscripted Han and non-Han astrology specialists from the astronomical institutions in Beijing of the former Mongolian Yuan to Nanjing to become officials of the newly established National Observatory. That year, the Ming government summoned for the first time the astronomical officials to come south from the upper capital of Yuan. There were 14 of them. In order to enhance accuracy in methods of observation and computation, Honggu Emperor reinforced the adoption of parallel calendar systems, the Han and the Hui. In the following years, the Ming court appointed several Hui astrologers to hold high positions in the Imperial Observatory. They wrote many books on Islamic astronomy and also manufactured astronomical equipment based on the Islamic system. The translation of two important works into Chinese was completed in 1383, Zij and Al-Madkhal fi Sinatakam al-Nujum, Introduction to Astrology. In 1384, a Chinese astrolabe was made for observing stars based on the instructions for making multi-purposed Islamic equipment. In 1385, the apparatus was installed on a hill in northern Nanjing. Around 1384, during the Ming dynasty, Honggu Emperor ordered the Chinese translation and compilation of Islamic astronomical tables, a task that was carried out by the Scalus Mashehe, a Muslim astronomer, and Wu Bozong, the Chinese scholar official. These tables came to be known as the Hui Lifa, which was published in China a number of times until the early 18th century, though the Qing dynasty had officially abandoned the tradition of Chinese Islamic astronomy in 1659. The Muslim astronomer Yang Guangxian was known for his attacks on the Jesuits' astronomical sciences. Career in the early Joseon period, the Islamic calendar served as a basis for calendar reform owing to its superior accuracy over the existing Chinese-based calendars. A Korean translation of the Hui Lifa, a text combining Chinese astronomy with Islamic astronomy works of Jamal ad-Din, was studied in Korea under the Joseon dynasty during the time of Sejong in the 15th century. The tradition of Chinese Islamic astronomy survived in Korea up until the early 19th century. Observatories. The first systematic observations in Islam are reported to have taken place under the patronage of Al-Mamun. Here, and in many other private observatories from Damascus to Baghdad, meridian degrees were measured, solar parameters were established, and detailed observations of the sun, moon, and planets were undertaken. In the 10th century, the Buwayhi dynasty encouraged the undertaking of extensive works in astronomy, such as the construction of a large-scale instrument with which observations were made in the year 950. We know of this by recordings made in the Zij of astronomers such as Ibn al-Alam. The great astronomer Abd al-Rahman al-Sufi was patronized by Prince Adad od-Dawla, who systematically revised Ptolemy's catalogue of stars. Sharaf al-Dawla also established a similar observatory in Baghdad, and reports by Ibn Yunus and al-Zarqal in Toledo and Córdoba indicate the use of sophisticated instruments for that time. It was Malik Shah the first who established the first large observatory, probably presumably in Isfahan. It was here where Omar Khayyam with many other collaborators constructed a Zij and formulated the Persian solar calendar aka the Jalali calendar. A modern version of this calendar is still in official use in Iran today. The most influential observatory was however founded by Hulagu Khan during the 13th century. Here, Nasir al-Din al-Tusi supervised its technical construction at Maragha. The facility contained resting quarters for Hulagu Khan, as well as a library and mosque. Some of the top astronomers of the day gathered there, and from the collaboration resulted important modifications to the Ptolemaic system over a period of 50 years. In 1420, Prince Ali Beg, himself an astronomer and mathematician, founded another large observatory in Samarkand, the remains of which were excavated in 1908 by Russian teams. And finally, Taqi al-Din Muhammad ibn Maruf founded a large observatory in Istanbul in 1577, which was on the same scale as those in Maragha and Samarkand. The observatory was short-lived however, as opponents of the observatory and prognostication from the heavens prevailed and the observatory was destroyed in 1580. Other sources give the rise of a clerical faction, which opposed or at least was indifferent to science, and specifically to the recommendation of the chief mufti of the Ottomans, as the explanation for the destruction of the observatory. Instruments. Our knowledge of the instruments used by Muslim astronomers primarily comes from two sources. First, the remaining instruments in private and museum collections today, and second, the treatises and manuscripts preserved from the Middle Ages. Muslims made many improvements to instruments already in use before the time, such as adding new scales or details. Their contributions to astronomical instrumentation are abundant. Celestial globes and armillary spheres. Celestial globes were used primarily for solving problems in celestial astronomy. Today, 126 such instruments remain worldwide, the oldest from the 11th century. The altitude of the Sun, or the right ascension and declination of stars, could be calculated with ease by inputting the location of the observer on the meridian ring of the globe. An armillary sphere had similar applications. No early Islamic armillary spheres survive, but several treatises on the instrument with the rings were written. In this context, there is also an Islamic development, the spherical astrolabe, of which only one complete instrument, from the 14th century, has survived. Astrolabes, brass astrolabes, were developed in much of the Islamic world, chiefly as an aid to finding the Qibla. The earliest known example is dated 315. The first person credited for building the astrolabe in the Islamic world is reportedly Fazari. He only improved it though. The Greeks had already invented astrolabes to chart the stars. The Arabs then took it during the Abbasid dynasty and perfected it to be used to find the beginning of Ramadan, the hours of prayer, and the direction of Mecca. The instruments were used to read the rise of the sun and fix stars. Al-Zarqali of Andalusia constructed one such instrument in which, unlike its predecessors, did not depend on the latitude of the observer, and could be used anywhere. This instrument became known in Europe as the Sophia. Sundials. Muslims made several important improvements to the theory and construction of sundials, which they inherited from their Indian and Greek predecessors. Khwarizmi made tables for these instruments which considerably shortened the time needed to make specific calculations. Sundials were frequently placed on mosques to determine the time of prayer. One of the most striking examples was built in the 14th century by the Muwakki of the Umayyad Mosque in Damascus, Ibn al-Shatir. Quadrants. Several forms of quadrants were invented by Muslims. Among them was the sign quadrant used for astronomical calculations and various forms of the Hori quadrant, used to determine time by observations of the sun or stars. A center of the development of quadrants was 9th century Baghdad. Equatoriums. The equatorium is an Islamic invention from Al-Andalus. The earliest known was probably made around 1015. It is a mechanical device for finding the positions of the moon, sun, and planets, without calculation, using a geometrical model to represent the celestial body's mean and anomalistic position.